This is day 4 for circular motion for Chapter 2, Physics 12. It's our third day of looking at free body diagrams, and we're just going to look at one last amusement park ride and see how F net equals ma plays out in this story. The ride itself comes under a few different names. Generically, they're called rotor rides, and it's like a big, gigantic drum that you walk inside through a little door. They shut the door and you find yourself a convenient spot up against the wall, and then they spin this giant drum and you're inside. And when you're in it, there's this feeling, this perception of you being thrown outwards against the wall. And they actually, on many of the rides, will drop the floor out and you're kind of smeared against the wall and you'll actually stay stuck there. Now, we know that it's a reference frame issue, and from outside, looking in, we can see that the wall is actually pushing them in. It's pushing against their backs, and it's forcing them towards the center, making them go in a nice circle. So let's take a look at one example here. There's the big giant drum, and here's some little kid in there, some little kid in a red sweater or something like that. They have some mass M. And it's going so fast that they're being smeared into the wall. The wall's pushing them really hard. They're actually stuck there just with static friction. And then, just looking back at the picture, they slow the ride down slower and slower, taking longer and longer to go around. Okay, so a lower velocity, bigger and bigger periods, until eventually you unstick. And then you kind of slide back down to where the floor is. So what I'm wondering is, how slow can we go? What's the smallest velocity? Or to say that another way, what is the largest possible period that you could have? What's the most time you could take to spin it around and still have them stuck there? So let's take a look at them as they're making contact with this wall and their feet are not touching the floor. I'm just going to draw their free body diagram here. You could draw it there if you've got enough room. There's definitely an mg pulling down. That's just the earth down there tugging down on them. And there's going to be a normal force. Normal forces are just surface forces. So the surface is the wall, and it's pushing on their back. And normal forces have to come out of the surface at 90 degrees. So the normal force will come out of the wall, push on their back. And that's actually what's going to make them go around the corner. Now what's holding them up is as that wall squishes in on them and creates that compression, we now have the opportunity for friction, stuck friction, static friction, to hold them up. So we're going to have a friction force here that will actually balance out with that mg to support them in the air. Now we're going to go through the example. The math is not very hard, but I'll caution you right away that it's going to be unusual to see a force of friction go vertical and an Fn go horizontal. We are so accustomed to seeing them the other way, and that's because we're accustomed to seeing blocks of wood lying on the ground, on the floor. Well, this block of wood is actually a person, and they're up against this vertical wall. And so the Fn comes out of the wall, going sideways, and the friction runs along the wall, and that's going to go up into the air. And as I stare at this picture, what I notice is that the normal force is all by its lonesome, it's all by itself, it's in towards the center, which is good, and it's going to make them accelerate. Let's see if we can go and find this largest possible period in order for them to just barely unstick. So this is static friction, but because of this word largest, it looks to me like they are right at the edge of unsticking. So I've got F net equals ma. Write it any way you want. You can write it this way, or you can actually just write F net equals ma. The net force based on the picture is actually the normal force. So I'm going to put that in for my net force. I'm choosing the period version for A because they're asking me, what is the biggest time you can take and just barely have them stuck? Okay, so far so good. I've got this Fn, but it's kind of hard. What should I do with this Fn? I'm not too sure. And so I'm going to go back to the story and go, okay, look, the friction that's there is just about to break free. I could go and use the equation, force of friction is equal to mu Fn. But again, it's going to seem odd. We are very accustomed to replacing an Ff with a mu Fn. I'm trying to replace an Fn. So you have to rearrange the equation in your mind, Ff equals mu Fn, and solve for Fn. And when you rearrange this equation to solve for Fn, you're actually going to have Ff divided by the mu. It is okay to use this equation because the grammar of this question says we are at the slipping point. So here goes. Out goes the Fn, and in goes Ff divided by mu. In this story, if you look back at the picture, the Ff is balancing the mg. You know, in any other friction story, we'd often say, oh, the Fn balances the mg, but not with this one. It's actually the friction that balances the mg. So I'm going to take the ff out and say, well, that's actually balancing mg. And here's where it gets really nice. Little kids and big kids are all going to stick the same way, assuming they have the same stickiness of clothing. We can actually cancel the m's and then keep on going. So at this point, we're going to go and look for that period. Yeah, sure, it's quadratic, but it's going to be easy. Just a little cross multiplying, find t squared, and then take a square root, and we should have it. So cross multiplying gets you to there, taking a square root, and you're done. You can rotate that giant drum every 3.59 seconds, right? It is a big drum. You know, the diameter is 16, the radius is 8. As long as you're spinning it that quick, with a period of 3.59 seconds or less, they will be stuck. But as soon as you go past 3.59 seconds, that means you're too slow, and then the riders will unstick and slide down. And that marks the end of our quest to go through all the different free body diagrams for circular motion. There's one story yet to go, and that's gravity and orbits. We'll take a day to look at gravity, and then we'll come back and do orbits.